Hello and welcome to the KIM-1 Resurrection Series, Part 4. In this episode, we're actually going to get to play with the KIM-1 itself. So, here it is. And a quick overview of the board. This is the 6502 processor. These are two Riot chips. That's ROM, RAM, I/O and timer. There's two of those. They're almost identical. The programs in the ROMs is different for each one, and you can't change it. It's all built in when the IC is actually made. So this is the lower one that you boot off, and I believe the code in this one is to do with this stuff over here, which is the tape interface and terminal interface. You can actually connect a terminal to this. These over here are the RAM chips. They're static RAM. And they're 1K by 1 bit each. So it's bit 0, 1, 2, 3, all the way up to 7. There's your oscillator. You only need the crystal with the 6502 and a few other little components there. For the actual clock part is actually done in the 6502, giving you a phase 1 and phase 2 clocks out of the processor. So the output from the static RAM goes to these ICs. The inputs of the RAM is connected to the bus all the time, but the outputs go through these buffers, feedbacks round. And you've got a display over here and a keyboard. So the keyboard on this one's been extended out. I'm going to take all that off and mount you back on the board as it should be. I know the reset key works. I know this switch here works. And there's a few other glue logic chips in here, and we'll have to start it up and get it running. One thing I've done on this board is you have to have, when you got bare board, to have this link here. It connects the 0 volts to one of the decoder ICs. That basically makes the 8K, bottom 8K addressable space repeat itself every 8K. When the 6502 starts up, it looks at the top 4 memory addresses to see where where to start from. 2 of them are the interrupt vector, and the other 2 a bit lower down is the actual startup vector for when the reset is pressed. So this is all configured in the board. So this chip here is actually the lower ROM space, or one of the lower spaces, actually repeats itself higher up, so we can actually get the address vector out of this IC here, which is in fact lower down in the actual memory addressing. Now that is this wire link here, this black link you see, that link I was over there to get it all to run, it's only on that side. So if you want to add anything that side, you have to fly in lead to go over here and another connector. Whereas a power supply can actually be connected over here. So putting that lead over here to that spare pin there, there's 3 spare ones, then I can use that pin there on the board to put the signal on there for the addressing decoder with just one board connected. So I've got a few different boards I made up in the past, and I'll be using them again. So here's some decoding and a RAM chip on it. Oh, and a bit of bodging on the back for different addresses. I'll just use the one board for several things. There's another one that's a bit different. It's got RAM and a ROM on it. And there's that link for there to simulate having that link over there. Oh, it's a little bit clearer on this board here. So we fitted flying leads on this one to connect straight to Logic Analyzer. We'll come to those later. We'll actually start looking at what's actually wrong. So let's do some tests. So let's start it up. The power's on and nothing's happening. I'll press the reset button. Pull in 530 milliamps a moment. Every time I press that, it changes slightly. If we go to single step mode, 540 milliamps. Press button and it drops to 520. So we know there's something working. So we put it back onto run and let's stick the scope on it. What I shall do, I shall put channel 2 screen onto that nice convenient 0 volts there. Then I'll use channel 1 probe because the 0 volts are joined together on the two probes. Now on the 6502 we've got a pin that pulses every time an instruction is operated. And let's see what pin that is. That's called sync. It's on pin 7. Right. 1, 2, 3, 4, 5, 6, 7. And then we've got nothing on the oscilloscope. Just reset. Oh, there we go. Let's slow it down a bit. So every time there's an operation, that pulse happens. So the processor's running. It's not necessarily running what we want it to run because the display doesn't seem to do anything. If I press the reset, you can see it's resetting. Go single step, it just stops. Press reset again, and there we go, we get a few pulses. It does about 11 instructions and then stops. I'm not sure if that's because it's got to a single step point or a broken bit of code. Because I know when I've had the analyzer on this before, we got some bits that don't seem to be working right. We go on pin 2. Oh, no, maybe not. Pin 3 maybe. Oh, there we go. That's the phase 1 clock. And on the other side we've got phase 2 clock. So I'll put both probes on, you can see them both out of phase with each other. Phase 1, and slow the scope down a bit so you can see it a bit better. And here we go on phase 2 on the other side. There's your two phases. Phase 1 is the yellow one, and phase 2 is the red one. The yellow one is when they do all the setting up, and on the red one, on the phase 2, that's when all the data is stepped into the registers. So the processor's running, but we've got nothing on display. And I press all the buttons, nothing happens. I'm not even sure if the rest of the keyboard works. Single step, no, nothing. We need to find out why. I think I need to put the logic analyzer on here now and see what the signals are doing. If we look at the overview of the KIM-1, we find it's quite a basic system really. We've got processor up here, 6502, and that's got some control logic with it. And that feeds down to the two riot chips. First one here, with bootloader ROM. It also controls the keyboard and display, and talks to the any tape or teletype, that's those analog part of the board. And then there's another riot chip here, which allows you to plug various peripherals in, whichever you want. You've got this application connector, which is one of those edge connectors. There's a bit more ROM in there that controls some more stuff. And then you've got 1K of RAM, which is those 8 smaller chips. So quite a simple system really. So we scroll down in the manual to the next page. We've got part of the address decoder in here. This part here, this 74145, you've got 4 inputs and 8 outputs. Now this is a demultiplexer. And you think, well, you only need A, B and C, which is the lower 3 bits, to get your 1 to 7 output. So do your 8 outputs, which is correct. We've also got this other bit here that there's I think there might be some more outputs, 7, 8, 9 and 10 I think. But when this input is at 0, these will operate and they pull down to 0. But when it's at a 1, so that comes down here, when that's at a 1, zoom out a bit more, then all these will be disenabled. So none of these is K0, K1, K2, etc. None of those will be on. All controlled by that one line there. This is that extra wire link that I showed you. When this is pulled down to 0, then address lines 10, 11 and 12 over here feed through to here, get decoded to give us our 7 different chip enabled, well, I say chip enables. They're each one of these is it's kilobyte 0, kilobyte 1, 2 in the memory address range. We'll look at the memory space shortly. Some of these are held up positive. So it's quite a clever way of enabling and disabling all this addressing just through this one bit here. So you can use this to add extra decoding to the address range to allow more memory to be added elsewhere. Now just popping back to the address decoding. Here's that address decoder up here. And the D line, remember we had to pull that down to 0 to make things work? Well, if you feed that out to another decoder chip and put the high addresses in it, so 13, 14 and 15 into here, that's got 8 different outputs. You put the bottom one onto there. When these are all 0, this will go to 0, and then you'll be looking at the bottom 8K. This is a full decoding. So then you can have like number 1 here. So if address bit 13 was on and the others are off, this output here will be high and disable that chip, because we want to disable the chip. It puts a 1 on there, and then the decoding is a different I/O pin which isn't used, or it might not even be a pin there at all. So all these will be turned off, and your chip control goes through here, and you can have another one of these the same as that. Notice it's on pin D as well, so you put the bottom addresses 10, 11 and 12 into A, B and C, and repeat that into these, and then this does these K numbers, 1Ks, there's a K8, K9, 10, so forth. You can keep doing that all the way up to the top, so there'll be 65, there'll be 64, that's numbered wrong, got that numbered wrong now. There'll be 64 possible different decoder signals up to K63. It won't be a 64 and 65. I'm not sure what they're doing there. There are a few mistakes on the documentation I've noticed. All the memory chips are numbered around the wrong way. It's one of them. And some of the pins on the 6502 are labelled wrong. So I'll be using a similar system to this to decode the extra balls that I'm going to plug in. I won't be doing a full decode, but I'll be doing some to make sure this doesn't come on. And I'll be doing some in-between bits, trying to put some RAM in, but not the ROM or vice versa, to try and test different parts of the other actual board, to check that the RAM's working, and see what we can fix about this ROM. So here, this is where we got the startup vectors. Let me zoom in a bit. This is the top of ROM. The 6502 will first of all go to this address and load in those vectors and store them away. And then it will collect this one, and that's the reset vector. That goes into the program counter for startup. The data stored in these memory locations is the startup address, so you can make it start up at any address you like. And then you've got these ones here is for the non-maskable interrupt vector. That's used for single stepping, etc. But when the processor starts up and it reads in its start reset vector and places that in the program counter, when it receives a reset, you'll go to that location, which is right just here, and it will start processing from here. And the first bit here is load the X register with FF. Forgot what that one is now. And then it'll be saving the X register out to the bottom bit of memory, etc. But as we'll see shortly, this bit here isn't working quite right. The code is fine, it's just we're not reading it properly. So here we have the logic analyzer put in a nice base now, 3D printed to stop it shorting out on anything, and there's a total mass of connecting leads to go with it to connect up. I'm just using 24 of them at the moment, and this bottom one's the 0 volts, and that one's the trigger that will be connected to somewhere, Probably on the instruction pulse that we saw earlier. So I'll get all that connected. Here we are, all wired up. Big mess of wires. Well, one thing I've found though with these ribbon cables is they do tend to pick up between each other. It's just the cheapo DuPont ribbon cable from China. I have got some other screened wire on order, and when that turns up, I shall be making some new leads that will be screened so they won't interfere with each other. And I'll make them longer, and they'll all be singles as well. So I'll make them a good foot long so I can reach over easy. Right, if we plug in the analyzer over here, plug in, there we go, and that over there. Up here on the control panel, we're on COM3, yep, and we'll go for 32 channel at 4 meg. I found the 8 and the 4 meg is where we get the interference, so I hope to cure that. The 4 meg should be good enough. I designed this just to be a 4 meg one. The 8 and the 12 meg ones are just a bonus. Right, I'll power up the board. So we're actually running now. Now I'll put the trigger on trigger to positive. I found this will trigger straight away. Press the reset down, and then arm, and then release the reset, and it's got a trigger from the first instruction pulse, from the first stream of pulses we're getting, and it's transferred it. There we go. The data's all ready, and I'll load that all into Pulseview now. We switch screens. Here we have the outputs from the logic analyzer. Set up the data and address, so the first set 8 bits here, D0 to D7, that's the data bus, and D8 onwards down to D20 is address bus. I haven't done the full address bus. I don't need the top 3 bits at the moment. What I have done is I've put D22 on phase 2, I think it is, and D23 on phase 1, or it could be the other way around. We'll find out in a moment. We've got here, we've got right, D22 is the phase 2 clock, and D23 is phase 1. Just as you can see, the pulses going on and off. And as you come along the bottom here, the address is on the bottom here, and the data are up here. So the address will be set up, and here's the phase on the phase 1, and all the data gets put into place, as you can see here. And this is the phase 2 clock, which when it drops at the end here, that's when the data is clocked in. So it gets loaded into whatever device the data bus is pointing at. So it's a bit of gibberish to start with. The 6502 does a few bits and pieces. There's 6 clock cycles before it actually starts processing. And the first thing it does is load the vector for the start of the program into the program counter. So it looks at addresses 1 FFC and 1 FFD for the reset vector. So the first one is the number 22, and the next one is 1C. So this is the high byte, and that's the low byte. So we got address 1C22 is put onto the address bus at this point here, and that is where we're going to start decoding the instructions. So if we look up on the actual listing I've got here, so we're coming in at this location just here, this bit of code. So it's 1C22, which is an A2 and then an FF. If we look at the actual code here, there's the address 1C22, there's the A2 being loaded onto the data bus. So that's our first instruction. And A2, the instruction A2 is load the X register. Come back over here. Oops. Is load the X register with this immediate value. So it's going to put FF into the X register. So we've got A2 sitting down here. when it starts to execute that instruction, the program counter has been updated and put back out on the address bus. So that's the next location, 1C23. We should have FF in it. Well, where we're reading it back here, we're getting BE. We should have all the bits should be on. You know, it's bit 6 is off and bit 0 is off. And when I've done this a few months ago, I can remember bit 0 being off, but not bit 6. So things seem to have got a bit worse. I did do some testing to make sure bit 6 was reading correctly on the logic analyzer, and it's fine. The logic analyzer is reading that correctly. So bit 6 is not coming on, nor is bit 0 of the data bus. Just so happens back here, we didn't use those data bits, so it ran through okay. So now we've loaded BE into the X register instead of FF. So if we scroll along a bit further to the next instruction, next one is right 1C24, and that should be 1C24 9A, and that is right TXS 9A. On my table it says transfer the X register to the stack pointer. So that instruction, where are we here? 9A. We've read 9A in successfully. Now it's going to transfer what we'd loaded in here, which is BE, which should have been FF, into the stack pointer. So the stack pointer is pointing to the wrong place in memory. It's now looking at BE. Should be looking at FF. So that's loaded in there. Next instruction, which comes from 1C25, is 86. And 86 is store X. Let's look that one up here. The description 8. We're looking at 8. 6 is store X in the 0 page. So store the X register. You get lots of movement on the address and data bus. If you actually look in the KIM-1 manual, it shows you what's going on, where the program counter's been stepped on, etc. And very often what's on the data bus is just totally ignored because it's not part of the instruction. It's just the next microcode step. Move along a bit here. Uh, 86, and it should be reading in F2. So 86 and the next address, 1C26, it's got a B2 there. That should be an F2. Again, the bottom bit is okay because it's F2, don't need that. But bit 6, just here, is still at 0 and it should be a 1. So we've now loaded B2 in instead of F2. Alright, next instruction should be, well, let's put B2 there. Okay, so we should be storing the X register in 0 page location F2. Well, we're actually putting it into B2. Now we know we've read the address in there from ROM, and now it's put it out onto the address bus. So we put address B2 out onto the address bus. So we know that's the data that definitely got read into the processor because it's just put it out again on different pins. So it's definitely reading it wrong. And the value that was in the B register, or the X register, was BE, which we had back here. So we read that in wrong. So we now put that value of the stack into the 0 page. So we put the wrong stack value into the wrong 0 page because of those bits. So this is all going a bit gaga here. So the next instruction is 1C27, which is jump, which has got number 20 comes in, which is jump to subroutine. And it's going to start loading that in. So it's 88 and it should be 1E. Roll along. Where are we? 88. And there's all sorts of bits going on where things are being saved onto the stack, etc. And then it loads in the other part of the address here, 1E. And we actually jump to the address subroutine 1E88 there, which has got A2 on it, etc. But the processor then goes off and does goodness knows what. We know it's running, but we've got the wrong return address on. So when it returns from there, it's going to return to the wrong place, and it's going to be all over the place. We need to fix those bits. Now, everything implies that the ROM is putting out the wrong code, but it could be the actual bus is stuck. What I think I'll do is I'll transfer this code onto a ROM chip, burn it in a ROM chip, and plug a card in with the actual code in. So make it so that it doesn't select the ROM chip that's on the main board, but it will select the ROM chip that's on the daughter board I plug in and run the code from there. And we'll see if we get any changes here. If it reads the right data in, then we know it's to do with the ROM chip, because the new ROM chip will be connected to the same data bus and address bus. We'll be able to determine whether it's the special ROM chip. If it is a special ROM chip, then we're in big trouble, because they cost the earth and they're like, well, you just can't get them anywhere. So in the next episode, we'll be modifying the ROM on this board and plugging it in to do some tests on the ROM sitting here. We'll bypass that ROM basically and use this one to see if we can check whether the data lines are working or not. So don't forget to put lots of comments below and like and subscribe. I hope to see you in the next episode.